NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, ladies and gentlemen. How's everyone tonight? Thank you very much. As always, thank you very much for coming out to join us tonight. The InSight mission to Mars, scheduled to launch in May 2018, will be the first NASA mission to observe the deep interior of Mars and help us learn about the history and evolution of the planet. The instruments InSight will bring are conceptually simple, yet also sensitive, delicate, and complex. The spacecraft itself uses proven hardware from previous Mars service missions, but also features new activities crucial to the success of InSight science. Our guest this evening will help us dig deep into the workings of the next Mars adventure. Tonight's guest exults in a lifelong love of space, rocks, science, and engineering, and is found in his role as a planetary geologist and instrument engineer at JPL, a perfect marriage of these interests. He received bachelor's degrees from MIT in both material science and engineering and earth, atmospheric, and planetary sciences. He then earned his doctorates at Caltech's Geological and Planetary Sciences Department, where he focused on investigations of the growth, evolution, and loss of subsurface ice on Mars. He has participated in a number of field campaigns to study life in extreme environments and to test prototype Mars instruments, from the ice caps of Greenland to the heights of Earth's stratosphere, places surprisingly similar to Mars. When he came to JPL in 2008, he served on the instrument team for the Mecha instrument on the Phoenix Mars lander, and since 2010, he has been a part of the science team for the InSight mission, where he is also the JPL instrument systems engineer for the lander's German-built heat flow instrument. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Troy Hudson.
Hello, and thank you for coming with me on this journey this evening. Over the past 2 decades, 11 missions have visited Mars. But our newest mission, InSight, will look at the red planet in a totally new way. From orbiters to landers to rovers, we've explored our neighbor's atmosphere and surface with ever-increasing levels of detail and sophistication. But, and to be a bit cliche, these missions have only just scratched the surface. There are many deep questions we have about Mars. As a planet, how did it form? How has it changed over time? And what is it like today? Mars is one of a family of planets, rocky planets. They're quite distinct from a gas giant like Jupiter, and different still from the trillions of comets and asteroids that still inhabit our solar system. They're a family, but they're a very diverse family. And one of the big questions we have is why? Did they in fact form from the same stuff? And once they formed, how have they changed? What brought them to where they are? Are there laws that govern the formation of a rocky planet? Maybe there are tendencies that they follow but can deviate from. And maybe coincidence played a role in giving us Mercury, Venus, Earth, Mars, and the Moon. Go back in time 4.5 billion years ago when the solar system was forming and planets were growing. As gravity brought together matter into clumps that grew over time, these clumps began to heat up. And when they got hot enough, they began to melt. Heavy things like iron fell to the center, whereas lighter minerals and elements rose to the surface. This process, this differentiation, is thought to be common to all such bodies, a birthright of terrestrial planets. And this process gave rise to familiar layers, core, mantle, and crust. And indeed, All of these objects share these features, but in very different ways. So with InSight, we will be going to Mars to look beneath the surface and see what it's like inside. Consider, though, for a moment that crust, the Earth's crust. Everything you've ever seen with your own eyes, every person, every living thing, every mountain, canyon, and ocean, all exist on the crust of the Earth. And that layer is thin. Size for size, Earth's crust is thinner than the skin of an apple. So much of a planet is unseen. And so with InSight, we will look with tools other than our eyes to find out what is Mars like as a planet. We know the Earth and the Moon pretty well. 100 years of seismology and geology have taught us a lot about what Earth looks like inside. We know it's a very warm place. There's a liquid outer core churning and moving, and this moving magnetic fluid, iron fluid, creates Earth's magnetic field. Earth is a very active place. We have volcanoes. We have the bane of Southern California of earthquakes. We have plate tectonics, a process which has recycled and evolved Earth's mantle and crust since it was formed. The Moon we know about because of Apollo. The Apollo astronauts went there, brought back rocks, and they left seismometers on the Moon. These tools continued to operate long after the astronauts had gone, bringing back over a decade worth of data of moonquakes. We've learned that the Moon, despite its early violent and active history, origins, is now rather cold. Solid throughout, there's no intrinsic magnetic field. Most of its activity was in the past. Because of its size, it didn't experience all of the processes that Earth did. It didn't get as hot, there weren't as high pressures. And so a lot of the early formation processes that happened on Earth didn't happen for the Moon. Mars, scientifically, is an ideal in-between, a Goldilocks planet, because it's big enough to have experienced those pressures and temperatures and a very active history similar to Earth's. But it's small enough that it lost a lot of that early heat. Whatever dynamo it had to create a magnetic field early in its life is now gone. It's stopped. Mars has frozen into an early state, possibly a state like Earth when it was young, before Earth erased that evidence with tectonics and convection. So by studying Mars, we get a glimpse into what Earth may have once been like. This chart shows you our current state of knowledge for major layers in the Earth and the Moon and Mars. But the key point here is to look at the numbers. The numbers for Earth and the Moon are just numbers. The ones for Mars have question marks. Our state of knowledge of Mars is informed by some information from satellites, some application of physics and geology, and our understanding of how those play together, but there are still big uncertainties. So we want to look into Mars. In the language of the InSight mission, we call these vital signs. We want to look at Mars's structure, and we will do that with Marsquakes. Much like a doctor can use ultrasound to look inside your body, we will look inside Mars with these planetary scale vibrations. We also want to take Mars's temperature, find out what is still in the planet that churns and creates geologic activity, and what was it like in the past. And Mars's reflexes. It spins in space, but it wobbles as it does so. And this wobble can tell us about the interior. I've hinted at the goals of the InSight mission, but here they are in concrete. Some of the things we want to know. We want to know the core. How big is it? What is it made of? And what state is it in? Is it solid, liquid, or somewhere in between? What is the structure of the crust and the mantle? And how warm is the interior? How much energy is there in that planetary heat engine that drives geology? These are great questions, but they're not easy questions to answer. Even if you had a ruler long enough and you were on Mars, you couldn't measure the thickness of the mantle. It's not accessible. And so we have to look to answer these questions in indirect ways. We do this with seismology. How powerful are seismic events on the planet? How often do they happen? And where on the planet do they happen? Then how does Mars's surface and body react to external influences, like a meteorite impact or the movement of its moon, Phobos? Again, how does it spin and wobble in space? And how does its temperature in the ground change with depth? These are our measurements to help us answer our goals. And there's not a one-to-one correspondence. Some of the questions and some of the goals work together. We can take multiple types of measurements to answer a single question, giving more robustness to that investigation and deepening our understanding. So to make these measurements, InSight has 3 primary instruments, and I'll be talking in particular about those: SEIS, RISE, and HP cubed. But before I get into them, I want you to have a look at the lander as it will look when it's on the surface and see that it's not just these 3 instruments. There's a whole lot of other things that make up InSight's payload. We have a robotic arm, we have 2 cameras, and we have a suite of environmental sensors. These devices help the primary instruments do their job and provide context for the data they take. First, I'm going to look a little bit at SEIS. And SEIS is an instrument that anyone who lives with earthquakes knows about. It's a seismometer. There you see it deployed from the surface of the lander to the surface of Mars. And SEIS is not just one seismometer, it's actually 6. There's 3 of a type called Very Broad Baseline Seismometers, or VBBs. There's the Short Period Seismometers, or SP. And these are all packaged together into a dense sphere about the size of a volleyball. You can see there on the left some of the engineers at CNES, the French Space Agency, which is an international partner with InSight, who led a consortium of international partners to produce this instrument, this incredibly sensitive instrument. SEIS is as sensitive as the best seismometers on Earth. So sensitive that it can measure displacements in the ground smaller than a hydrogen atom. It's also robust. It can survive the rigors of launch, interplanetary spaceflight, and the temperature fluctuations on the surface of Mars. It can survive these things, but it's so sensitive that we still have to protect it from noise, from signals that would swamp out the weaker quakes and shakes and motions of Mars's surface. Some other components of SEIS, like the electronics box and the tether, help it do its job, connect that seismometer back to the lander. But I really want you to draw your attention to that figure at the top, where the seismometer, that golden volleyball, is inside this copper hexagon of insulation. That protects the seismometer from some of the thermal changes it would see on Mars. That's what you will see picked up off the lander and placed on the ground first after we arrive. But it's not enough. We need more protection, both from the sun and also from wind. Mars's atmosphere is quite thin, but it's still enough to shake and jitter that seismometer to the point where we couldn't get good data. So we have something called the wind and thermal shield, that white dome on the upper right. This is picked up by the arm and placed on top of the seismometer. And that golden skirt you see around the bottom, that's actually chainmail, just like you would find on a medieval suit of armor. We have that so that it can conform to the irregular ground surface of Mars and essentially prevent drafts from getting underneath and disturbing SEIS. Once we've got rid of all those noise, what are we looking for? We're looking for Marsquakes. How do we know there are Marsquakes? We've seen faults. Just like the San Andreas, we see places on Mars where the ground has moved relative to itself. We've mapped these. That figure on the lower left has some red and green lines showing where there are faults on Mars. And by combining these observations with our knowledge of geophysics and how it operates on Earth, we predict what kind of seismicity, what frequency of event we might see on Mars. In that chart, there's a red line. That's quiet places on Earth. Not ring of fire like we have here in Southern California, but quiet places. The magenta line, the pink line there, that's the moon. Mars, Goldilocks again, is somewhere in between. At the top, you see some numbers, the familiar Richter magnitude scale, and what this plot says is we predict somewhere between 10 and 100 Richter 5 Marsquakes, every year. For a magnitude 6, it would be somewhere like 1 to 10. That's this prediction. Mars could surprise us. It could be much more active, or it could be much less active. Either way, it's an interesting scientific result. But we have other things that we will be looking at with SEIS which are more definite and still tell us about the planet. One of these is the tide of Phobos. Phobos is the larger of Mars's 2 moons, but it's small. It's a lumpy potato, 27 kilometers in its biggest dimension. That's the distance from Pasadena to Santa Monica. It's tiny, but it's so much closer to Mars than the moon is to Earth that as it passes overhead, its gravity causes the ground on Mars to rise and fall. This is not something you'd ever feel, not something you'd ever see, but SEIS can. And by looking at this regular motion of the ground as Phobos passes overhead, and we do happen to land on the equator, so it passes right overhead, we learn about Mars's interior. There's another source of excitation, which again is Mars's atmosphere. It's thin, but it has regions of high and low pressure, and as these pass over the surface, they also cause it to flex up and down. This excites modes like a ringing bell and makes Mars hum, a seismic hum, which Earth also experiences. But here's an instance where studying another planet teaches us about Earth. Mars has a seismic hum because of its atmosphere. So does Earth. But Earth also has oceans. And the waves crashing into the shores and the swells from sea storms and the tides, these create an oceanic hum. But on Earth, they're mixed up together. It's hard to separate the two effects. So by studying Mars, we can see what's the effect of an oceanless planet. And then we can learn more about how Earth's hum works. Another source, the last source, and probably the most dramatic, is the impact of meteorites. We have orbiting spacecraft at Mars that are taking pictures of the surface, and every now and then we'll see, oh, look, a new dark spot. That wasn't there in the previous images, it's new. And the impact of meteorites on Mars is happening today, actually somewhat more frequently than on Earth. The thinner atmosphere lets a lot of those come in and make it all the way to the surface. A meteorite impact has a particular character. It's a bit different from an intrinsic, internal Marsquake. SEIS has those 6 seismometers that can detect not only the direction from which a seismic signal is coming, but the approximate distance. With that information, we can send the orbiting spacecraft to go look in that area, look for the new dark spot. Once we find that, we have a location, an exact time, from the size of the crater, we know the energy, and a perfect correspondence between observation and our ground truth from the seismometer. This is exactly the sort of information that we would use to make and change our models of what Mars is like inside. Here's an animation looking inside Mars for a meteorite impact, but it could be for any seismic source. The event happens and waves spread out through the planet. Pressure waves, compression, shear waves, shearing. They interact with the surface, they reflect across boundaries like ripples in a pond or light in a prism. And we can study the character of these waves where they arrive at the seismometer and change our models. That's the goal here, is to use physics, use geology, and make our model of Mars exactly match our data. That's the real goal, because the models can change. The data, that's real, that's physical, that is the world. So that's our seismometer. The next instrument that was mentioned is RISE, and RISE is the thing that will be looking at Mars's wobble. As it spins in space, it doesn't spin perfectly evenly. It does wiggle and wobble around. And it turns out this wobble carries information about the interior of Mars, its core in particular. RISE is part of InSight's telecommunications system. It has two antennas that send a tone, a single frequency, back to Earth. And by listening to this tone and the small changes that happen as Mars rotates, we can very precisely measure the distance between the receiving station on Earth and the InSight transmitter. Not just very, extremely precisely. Within 10 centimeters for something that's millions of kilometers away. That's incredible accuracy. Not only will RISE allow us to make this measurement once, we will make it continuously. For the entire time we're on Mars, we'll be making RISE measurements and extending that baseline, improving our knowledge of Mars's deep structure. The last instrument I'll speak of is HP cubed. The heat flow and physical properties package is the instrument I spent most of my time working on with InSight. And so I'll delve a little bit more deeply into the science and technical aspects of this literally groundbreaking instrument. You see the support structure of HP Cube deployed on the surface, and what you see there is the heat flow probe of HP Cube has already started its journey penetrating into the ground. Looking a bit closer at that structure, there's the grapple hook at the top, which we'll use for the deployment, and the engineering tether at left, which connects it back to the lander. Within that structure, we have a few sensors, and then there's a tether which connects to the mole. And that mole has a mechanism for hammering, it has tilt sensors, and it has some instruments for measuring thermal conductivity. But why? Why dig? Why a mole? Why did we need something that goes even deeper into Mars than we have with the other instruments? The purpose of HP Cube is to measure heat flow. And heat flow tells us about both the thermal and chemical history of the planet. Remember, when the planet formed, it brought in matter under gravity, and that matter included radioactive elements. These unstable atoms, as they decay, release energy, and this energy becomes trapped in the planet. It's one of the major sources of the primordial heat. We understand the physics of radioactivity quite well, and so we can look at how Mars is today and figure out the inventory of radioactive elements in the past. Are they what we expect for where Mars formed relative to the Earth and the Sun? Or is there something different, some reason why we need to refine those models? We want to understand the thermal history and how those radioactive elements have changed Mars's heat engine. And what's it like right now? How much energy is there to drive present-day geologic activity? To measure this heat flow, we need two numbers. We need thermal conductivity, which is a property of the ground, and we need to measure the thermal gradient. That's how the temperature changes as you go deeper. This is why we need the mole. We need to get down into the ground to avoid things like surface disturbances. Just like size, we don't want to see the temperature differences at the surface. We need to get below that. And so the mole will take us deeper than we've ever gone, human or robotic, on any other body. The Apollo astronauts, in their spacesuits with big hand tools, got down to a little less than 2.5 meters. We're targeting 5. That's 16 feet. That's taller than this building. And once we're there, we want to measure those temperature differences for that thermal gradient to within 1/100th of a degree. So there's some really key engineering challenges that we needed to solve, and the star of HP Cube's engineering feat is the mole. The mole, it's a small device. It's about the diameter of a quarter. It's about as long as my forearm. And it doesn't weigh that much, maybe about 1.5 kilograms. Main components are a hammer and some springs, a motor that winds up that hammer against the springs, and then what you see in this movie at the left is that instant of hammer release. When the cam is wound up, the hammer strikes and drives the mole into the ground. There's a few secondary strikes and settling, but this instant of hammering is what makes the mole move forward. This is slowed down. It takes about 1/10 of a second. And each hammer stroke, as that cam goes around, is about every 3 to 4 seconds. So imagine you're on Mars. It's a very stately pace, but millimeter by millimeter, we penetrate Mars's surface to do our science. Some statistics and other information about the mole. We've got our 3 seconds per hammer stroke, and then we don't penetrate all at once. We have cycles where we penetrate, and then we pause. The penetration process creates a lot of heat, and we let that heat dissipate. And then we heat the mole itself. Built into the structure of the mole are heaters. And by heating the mole up and letting that heat diffuse away into the ground, we learn the thermal conductivity. We determine that thermal property of the soil, which is key to that heat flow measurement. It takes about 24 hours to make that thermal measurement, and then we hammer again. 10 times we hope to do this, stair-stepping our way down to 5 meters on Mars. The mole might encounter a rock. We're going to a place on Mars which is relatively rock-free, but it's still possible. We've seen in some laboratory experiments that the mole can push small rocks out of its way underground. Larger rocks, the mole gets deflected a little bit and the rock gets deflected a little bit. Still larger rocks, the mole itself can deflect. We use the tilt sensor in the back of the mole combined with a measurement of the tether that gets pulled out to reconstruct its path in the ground. We do this because we need to precisely know where those conductivity measurements are made and where the temperature sensors that the mole pulls behind it end up. This is a time-lapse video, and in the very quick moment, you'll see the mole at the bottom. It's at the top of a slow column, and it's going to disappear. There it is. It started to dig. This is a column 5 meters tall in Germany where we are testing the operation of the mole. That plot at the right with the green line, that's the progress from this test where continuously we reached 5 meters in 5.5 hours. And this is in one of the more difficult materials that we use to simulate Mars's surface. So the mole's quite a capable thing. As it goes down, you might see these little white specks going down on the tether. Those are temperature sensors, 14 of them embedded in the tether. The tether itself is a scientific instrument. So the mole brings us down into the ground, measuring that key thermal property, conductivity. Once it's down, once we've reached our final depth, which we hope to be 5 meters, but we can do our science if we only make it a little bit shallower, the mole has done its job at that point. It's done. The remainder of the time on Mars, we monitor. We monitor temperatures with that science tether. One thing you might see is in the tether you have those little markings on the left and the right, those little dots. That's code. That's what that tether length monitor uses to measure the amount of tether that's been pulled by the mole into the ground so we can reconstruct the path of the mole, but also so we can reconstruct exactly within a centimeter where those temperature sensors end up with depth. And that's important. because we need to determine that number, that thermal gradient. At the bottom of that graph there, that line, that's what we're after. Closer to the surface, 1 or 2 meters down, there's still a lot of fluctuation. Annual, seasonal changes propagate into the ground, and they're noise for us. And so, with the mole, we dig. But first, after InSight has arrived on Mars, after we've gone through the 7 minutes of terror and landed on the surface, and the lander's healthy and doing fine, the instruments still aren't where they need to be. They have one last journey. Seismometer can't do its job on the lander. It's too noisy of an environment, especially with those big solar panels flapping in the wind. And HP cubed, capable as the mole is, you do not want to dig through the body of the spacecraft. So we have the robotic arm. And what you'll see in this next video is a bit sped up how the arm will deploy first the seismometer, then the wind and thermal shield, and finally HP cubed. Now this is sped up, so the process of picking up one of these items and putting it back on the ground takes about 10 minutes. But this video, or this animation, has also been severely edited. There's a whole lot of back and forth between Mars and Earth, making sure we grappled the object correctly, making sure we placed it correctly, and all of the other checkouts and cross-checks we do to make sure we get it right the first time. Here, the arm is picking up the wind and thermal shield in that skirt, and its legs just drop right down, and it comes over and gets placed on top of the seismometer. The arm doesn't have a huge reach. There's a small workspace in front of the lander there that it can go to. And we have preferred places where we'd like to put these instruments. But there could be a rock. There could be several rocks. We have to take pictures of the area and then decide exactly where we want to put the instruments. It seems like simple. This whole process seems like a simple thing. But it's complicated, and this is the first time we've done it. We've never deployed an instrument from a spacecraft onto the surface of another body before. We've had instruments on the end of the arm, but we've never done something like this. Here you see HP cubed getting placed on the ground, and the whole process from landing to this point here, where HP cubed is on the ground and the mole can start digging, will take about 45 days, in the best of cases. And so InSight is a mission to Mars. We will be studying Mars, we will be learning about its interior. But by extension and by comparison, we are learning about the other rocky planets in our solar system, the laws that govern their formation, the tendencies they follow, and possibly what coincidental chance events led to them being the way they are today. And we have discovered around other stars, other rocky planets, other members of that family. And we will, through this mission, gain insight into that formation process which could happen all over the universe. I'll spend a few moments now talking a bit about where InSight is at the present and what you can expect to see in the coming months. The spacecraft has been built. It has been packaged up and it has been sent to Vandenberg Air Force Base here in California. This will be the first time a mission, an interplanetary mission, has launched from Vandenberg. Our scheduled launch period is in May and June, and our first target launch date is May 5th. Once we launch, we'll cruise to Mars for about 6 months, landing on November 26th, 2018. This is that 7 minutes of terror, where we come through the atmosphere, first on a heat shield, then a parachute, then a brief moment of free fall and retro rockets that bring us gently down to the surface. Very much like the Phoenix Mars lander arrived in the polar regions of Mars in 2008. InSight might look familiar because it is based on the Phoenix spacecraft. Once we've arrived, we'll do our checkout and that whole deployment process. We'll calibrate the instruments, HP cubed will penetrate, and then the whole system goes into its listening mode. We listen to Mars for its quakes, we listen to its temperature, we observe its wobble. The primary mission for InSight is 1 Mars year. That's 2 Earth years. And if our history with engineering such spacecraft is any indication, for instance, the Opportunity rover was designed to operate 90 days on Mars, and it just celebrated its 5,000th day operating on Mars. InSight could be going for a decade or more. We'll be landing at a place on Mars called Elysium Planitia. It's quite close to where Curiosity is right now, exploring Gale Crater. We chose this location because it's safe for the lander, and it can let the instruments do their jobs. When we get those first pictures back, they're probably going to be the most boring pictures you've ever seen from the surface of Mars, because it's smooth and flat and boring, and that's exactly what we want. SEIS is studying the planet. It could do its job from anywhere. HP Cubed, also studying the planet, but it wants broken up regolith, broken up ground to dig into. It can't dig through rock. And so with those constraints and the various engineering constraints of the lander, we've chosen this location that will be our home for a long time once InSight arrives. InSight will not be alone on its journey to Mars. It will be followed by 2 CubeSats called MARCO. CubeSats, they're small, literally this big. And it's the first time one of these microsatellites has gone on an interplanetary mission. MARCO will act as mirrors, radio mirrors, receivers and transmitters, relays for the InSight lander as it comes through the atmosphere to land on the surface. We have orbiters around Mars right now that can relay signals, but they can't do it simultaneously. They can't listen to the lander and send the information back to the Earth. InSight will be on autopilot as it goes through the atmosphere to land, but MARCO will be able to relay all the information it gives us in real time. Well, as close to real time as you can get when you're many light minutes away. And now some of the things we've been doing to engage the public and everyone who is part of this mission. There's a microchip on InSight, 2.4 million names on it. Many of you in this room may be going to Mars this way. Many of you watching may also be going, and we thank you for that, and we hope you enjoy the ride. Here in California, we'll be doing a road show. We'll be taking some exhibits and some scientists and engineers to various locations in the months leading up to the launch. So if you're in these areas up in Shasta, San Francisco, Sacramento, and the towns along the coast near Vandenberg, there'll be a number of events that you can go to and get some more hands-on feel for InSight and the exciting engineering and science of this mission. And finally, please follow us on our journey to Mars. You can watch the launch online. I think there's now a Google Earth widget where you can see the flight path of the launch vehicle. You see if you can see it from where you live. And there's an app called Be a Martian. This will be returning data from InSight. The first data, once the instrument's all calibrated, will come back in March of 2019. You can get a notification on your phone. There's been a Marsquake. Here are the current conditions at the InSight lander and more. So you can look on the NASA website, you can find us on Facebook, and you can follow us on Twitter and continue to be a part, as you have been with me this evening, on our next journey to the planet Mars. Thank you. I would be thrilled to take your questions. If you would, there is a microphone in the center of the aisle if you'd like to come up to that so that those on the broadcast can hear your question as well.
Yeah, I have 2 questions. I hope they're brief. The first is, does the grapple have a job after it's deployed the 2 instruments?
The grapple itself, no. We don't have anything for it to do, but the robotic arm itself has a scoop on the end of it, and we may do some geologic investigations of the surface soil with the arm after it's deployed the instruments.
I assume when the mole is digging that the seismometer can hear it. Does it make enough signal to hear reflections from the internal parts of Mars?
Oh, that's a fantastic question, and it's particularly relevant because just this Monday, we went out to the field to do some preliminary geophysical surveying of a site that we will use to test mole seismometer interactions. They're not designed for this. The signals that we get from the seismometers are quite long period, and the impact of the mole is too fast for the seismometer to see in full detail. So we have developed some techniques where we can take advantage of this known seismic source. By taking various spectra every time the mole hammers and stacking them up, we can get a picture of what the near subsurface is like. We can't learn about the deep interior, but we might learn how deep is that soil we're digging in, and where is that first reflector, that first piece of bedrock? And that's a nice piece of information for the seismometer to have. So we're working to really understand that process, so when we get to Mars, yes, we can use HP cubed as a known source for size.
Hello, thanks for the talk. Have you an estimate of what is the chance of there being like a big rock underneath that you can't drill through?
We have. So we've looked at the surface and using information from other geologic sites on Mars that we visited with landers, and also looking at evidence from craters in the nearby region, we can estimate the distance to the bedrock and also the rock abundance. And we think for very conservative assumptions, the chance of us encountering a 10-centimeter rock is on the order of 73% in the 5-meter depth. Now, we encounter a 10-centimeter rock. That isn't to say that'll stop the mole, because depending on the shape of the rock and how it's oriented, we may pass by it entirely. So, and if you take less conservative assumptions, our chances of success go up to the high 90s.
Hi, great talk. I have 3 questions. One is how long does the mole have to stop pinging before it settles down and you can take temperature measurements?
So in the digging process, you mean the measurements of the tether?
Yes.
Yeah, so the process of digging itself injects heat into the soil. And we do need this heat to dissipate, and it will depend in part on how conductive Mars's surface soil is. If it's at the high range of the conductivities we expect, by the time the mole gets to the bottom, we'll be able to take good data. If it's at the lower end of the range, we may need to wait a few tens of sols, but not longer than that.
Okay. Second thing is what consequences is the possible communication problems with MRO, the Mars Relay Orbiter, going to have on you? I mean, you have 2 things communicating directly to Earth, but it's just tonal stuff. For the data that you're returning, you need to shoot it up to MRO, I presume.
Yeah, we need a pretty big pipe
Right.
to send that data back, because there's quite a lot of it. And MRO is only one of the orbiting assets that we can use. We can use Mars Odyssey as well, which is still in operation. It's getting a little long in the tooth, but it's still there. And then there's MAVEN, the MAVEN spacecraft that observes the atmosphere, and that can also act as a relay.
You can use all 3. Mm-hmm. All right. And the third thing is just, I have a sense, okay, let us take this and put it in my backyard, right? And have the thing go down 5 meters into my backyard. And suddenly, from this, well, not suddenly, but over the course of, let's say, 2 Earth years, I can ascertain the structure of Earth, albeit we have, plates floating around and it's a lot bigger and so on. But it just seems to me this is extrapolating enormously from a very small instrument, a very small suite of instruments in single place and Mars.
Yeah. Well, 1 is infinitely larger than 0.
Yeah.
You can, the seismometer is the thing that's looking at the overall structure of the planet. The mole, as an instrument, is looking at the local heat flow properties. And this needs to be matched then to models of Mars that say what the heat flow might be like at different locations depending on crustal thickness, which is something that SEIS can tell us about. Maybe the presence of mantle convection with SEIS can also tell us about. So these measurements work in concert. On Earth, Earth is a very complicated place. And to get good geothermal measurements, for instance, you have to go below the water table. You have to get below any kind of fluid circulation, because Earth has lots of water, and that really messes up those kinds of measurements. So there are aspects about Mars that make it easier for us, but the key point is this has never been done before. We've never made these kinds of measurements of heat flow anywhere on Mars. We've never had any seismometer, and there's quite a lot you can do with only one seismometer. You can pinpoint the epicenter of something with a seismometer as sensitive as this that has those multiple seismometers. You can determine the direction and the character of the signal. There's a bit of a bootstrapping process where you refine your models of Mars, but the old days of needing 3 seismometers to pinpoint the epicenter of a quake, you don't need that anymore.
Thank you.
You bet.
Thank you for taking us on this exciting journey. Lady Rocket, CEO and founder of California Space Center and co-founder with Grant Blaisdell of Copernic Blockchain Technology with Copernic Token, which mission is to seek space projects, hopefully like yours, to provide incremental funding should funding originally budgeted for the project is not sufficient. This is using power of cryptocurrencies to put it behind the industry that needs to get funded better by us Americans. May I ask you a question? If you would be willing to share some of your dreams that are aligned with what else would you like to accomplish during or after the Mars mission if budget was available? And let's see if we can make it happen.
What I would like to see personally, or what we would like to do with this mission?
How about both? Because you deserve personal dream fulfillment too, doing what you do. So give us both. But Copernic's mission is to seek those projects which carry incredible value but do not make it into the traditional budget, and see if we could bring incremental funding. So looking at that, or potential commercialization of what you will be generating there, so we could create an enterprise around it.
Well, there's a number of aspects of this. I mean, InSight was a mission that was competed within NASA. It was proposed, along with many other missions, to be awarded the funds of the Discovery program. And InSight was one out of many missions submitted and 3 finalists that ultimately got that funding. And so there are other missions that NASA decided these are good enough that we want to look more closely at them, but they could only choose one winner. And these are all great science and great engineering. And I mean, my personal favorites are things like, I study planets, I study geology, I want to know about Mars, and I want to know about asteroids and comets. And the idea of going to visit an asteroid or a comet and to bring part of it home, both from the scientific perspective, but also potentially to use it. Can we make something out of this resource? I'm an explorer. I love going to places we haven't been yet, and that's one of the things that excites me about InSight.
Thank you. And just thank you for mentioning Vandenberg Air Force Base in your presentation. They are an incredible team. Not as visited as Florida. I just came back from Vandenberg SpaceX rocket launch, and looking forward to seeing you in May. Thank you.
Thanks. I also saw the rocket launch this morning. All right, so 3 questions. First, does the mole have a method of being retracted in case you run into too many rocks?
It does not. The mole only goes one way, and that's forward. And hopefully that's also down.
Yeah, let's hope so too.
There were some early designs about a way that we would be able to reverse the mold to come back, but that's not part of this design. It only goes down.
All right, thanks. Second question. Why was Vandenberg chosen over KSC? And I hope you guys launch in the evening again to freak out LA again.
It turns out that our initial launch time is around 3 or 4 in the morning. So get up early and you might be able to see something pretty amazing. Vandenberg was chosen, I think, primarily because the schedule of launches at KSC in Florida was such that it wasn't possible to fit it in the time period where we wanted to launch so that we can land at the correct time. It's also possible because InSight is going on a very powerful rocket that has enough lift capacity to take us from this site, which is a little less favorable than the one in Florida, all the way to Mars.
All right, thank you. And the last question, would you guys consider using a Falcon Heavy for future Mars missions?
We did, in fact, consider using the Falcon as one of the potential launch vehicles for InSight. That was an option that was expressed in one of the original proposals. We ultimately didn't settle on that. It wasn't developed enough for us to use, but it's a possibility for future missions.
All right, thank you.
Hello, thank you very much for the enlightening talk and for giving me a chance to ask you a question. I hope this is not too tangential to the main theme, but it's, ever since I was very young, I've been following with great interest all of these projects to send probes into space, especially to Mars. And now it's getting to the point where, well, we've seen quite a few of these projects, and especially those landed. What it kind of bothers me that, up till now, there's been very little collaboration between all of these different projects. Is there any plans for this particular project to collaborate with any past projects or any future ones? What I'm thinking about in particular is that I've just returned from living in the United Arab Emirates in Dubai. I was teaching at a technical university there called the Khalifa University of Science and Technology. Don't know if you've heard of them yet. They are trying very hard to be the Caltech or MIT of the Middle East. And they've also come up with a very ambitious project to put a probe on Mars themselves. For a little country like that, I was astounded when I first heard about that they had these plans. I have to say that I'm embarrassed that I don't remember the details. What is the time frame? I think it's within the next 3 years or so. So my question is, are you aware of that? Are you aware that there is this plan on the part of the United Arab Emirates to put a probe on Mars? And again, is there any plans to coordinate with them on this?
I personally have not heard of that effort, and I do wish them the best of luck with it. Going to Mars, going into space is a difficult endeavor. And NASA, in this project in particular, but for all of them, is a collaborative place. We collaborate, the engineers and the scientists communicate across missions, learning lessons and making sure that mistakes aren't made again. InSight uses the Phoenix lander, so much of that engineering knowledge that was gained in the production of that spacecraft has gone into this mission. And as I mentioned, InSight's instruments are contributed by our foreign partners. The SEIS instrument was built by a consortium led by the French Space Agency, which includes a number of different European countries. HP Cubed, built by the German Space Agency. So collaboration is not a foreign thing for NASA. But how a collaboration comes to be, who needs to be involved in making that a reality, and keeping it going once it's birthed, and see it all the way through to the end when you arrive on Mars, it's a complicated thing, but it's something that we do.
Thank you.
Mm-hmm.
Hi, thank you for the presentation. If I understood you correctly, and I very well may have not done so, the launch window begins May 5th, but I thought I understood you to say that it could launch later in May or in June, depending on, I assume weather or other complications.
Exactly.
But the landing date is November 26th.
Mm-hmm. It's a consequence of how the orbital dynamics work out. We can, in fact, choose a very precise landing date and still have a window of possible launch opportunities.
So regardless of when it launches, it will land on November 26th?
As long as it launches in that period of a month and a half, yes, November 26th is the date.
Okay, thank you.
Mm-hmm.
Viking was landed in June 1976.
Mm-hmm.
Now this will be 42 years later, practically. And I remember Al Hibbs was talking about the Viking, and it was the first time. And I'm sure that few people here have seen him like that. I'd like to know what the technology evolved, how much it evolved from the Viking until InSight, and what do you expect? And you have 42 years, and we had different missions in between, as you know, okay? And what is the technology? And I don't know, I mean, I wish Al Hibbs was here today to see the improvement, the big improvement on the thing, and what you expect in the future.
Oh, there's so much that has changed in our ability to do planetary or any space mission. For instance, the seismograms that SEIS will record, we wouldn't be able to, we can't even now send those back in their entirety. We have to compress that data and send it back a bit at a time. And so the intelligence in the lander, in the SEIS electronics and the lander itself, can look at those signals, pick out interesting events, compress them and send them home. And that computing power is one major advance. The seismometer itself, Viking had a seismometer, did you know? There was a seismometer on Viking, one of them, because there were two Viking landers, one of them did not work. Its launch lock mechanism, I don't think, disengaged, and so it never saw anything. The other one saw things, but it was pretty much just the lander shaking in the wind. It made it all the way to Mars and never got off the deck, because they didn't actually have a way to deploy that seismometer onto the ground. And so the principal investigator of InSight, Bruce Bannert, has been advocating for a seismometer, and many geophysicists have been doing this, advocating for a seismometer and other geophysical instruments to go to Mars for a very long time. And we now have an instrument which is as good as the best seismometers on Earth. And that's just two examples, computing power and the seismometer. So many other things also have improved. And for the future, I would expect that it's going to be a long time before anything about exploration is plug and play, and it may never be so. We're never going to get to the point of having a Star Trek tricorder and just be able to do everything with one little device. We have to design things for the specific environment, the specific constraints of the mission, and in particular, the specific science questions. Because every time we design a mission and we send it somewhere and we get the data to answer those questions, we get more questions. That's what science is about.
The day Viking landed was my first day at JPL, starting at JPL.
Very exciting.
Yes.
My first day at JPL was about 20 days before Phoenix landed. So it's a great way to start.
You mentioned that you expect to see seismic response from the passage of Phobos overhead. And that's really amazing considering how small it is. And so my question is, I've never quite understood, yes, you have Phobos as this little rock, and it could have been an asteroid, but it's in a more or less circular orbit. And how do we speculate on how it got there? And I've also heard some rumors that Phobos may not be around too many million years in the future.
Yeah.
And maybe you could say something about that.
So when an object is in an elliptical orbit, and when an object is spinning, the gravity of the planet it's orbiting can pull and tug on that object. So Phobos itself has been spun and turned in different ways by Mars's gravity. And this movement of the object isn't just a rigid body. Phobos is big and rock is flexible on those scales, and that dissipates energy. Energy gets dissipated as heat. That energy actually comes from Phobos's orbit. An elliptical orbit has more energy than a circular one, so over time, as the energy of the orbit gets dissipated away as tidal heating, both in Mars and in Phobos, the orbit circularizes. And it also decays with time. And this is what your second point. Over time, this captured asteroid, which is probably the origin of Phobos, will approach Mars closer and closer. And when it gets close enough, it'll pass a certain point where the tidal forces overcome the strength of the rock, and Phobos will break up and probably, for a few million years at least, be a ring around Mars.
Cool, thank you.
Mm-hmm.
Hi, thanks for the lecture. I came with my dad, who's in the front. He's a big nerd. This might be opening up a huge can of worms, but I was just kind of wondering about the design process for you guys and how you collaborated and prototypes, and if something didn't work, how you pivoted from there.
That's basically what JPL does, is solve those kinds of problems. And for every kind of problem, and I'm talking big categories here, whether it's developing a communication system or, like one problem, the seismometer. The key components of the seismometer, those VBB, are inside an evacuated container. Even Mars's thin atmosphere is too much for these really sensitive devices. They have to be in a vacuum to work properly. We had trouble making that vacuum stay there, because it has to be there when we assemble the spacecraft, make it all the way to Mars, and stay that way for at least 2 Earth years. We had problems, we had leaks, we had things we had to figure out, and there was lots of ways that we approached that problem. We created prototypes in the lab, we built things, and then we cut them in half and destroyed them to understand why they failed or why they worked. We tried different solutions. We formed teams of people, both here at JPL and with our international partners, people whose only job, these tiger teams, their only job is to focus on that problem because it's a big problem. So, and you know, we designed it first. We didn't expect it to leak, but it turns out that it did. So there's a lot of times where things pop up that you don't really expect. And, you know, learning lessons from previous things, having experts, people with their own internal knowledge and then the knowledge of the institution, those are all things that make this possible. You know, and as best we can be, possible on time and within budget.
And I was just wondering how long you worked on this project for.
I'm sorry?
How long you worked on the project for. I was just wondering.
I've been part of InSight since it was a proposal, when it was the discovery proposal in 2010. So about 7 years I've been working on this. First as a science implementation engineer, sort of working with the whole payload section, and then focusing more down on HP cubed. And I've been working with the German Space Agency and serving as a liaison between them and JPL and Lockheed Martin, who built the spacecraft, for about 6 years now.
Thank you.
Mm-hmm.
Hi, thank you for the lecture. How well would these instruments work on an asteroid or a smaller body with less gravity?
Yeah, so size might work a lot better in some respects. On a smaller body, there's, well, I want to take that back. I don't actually know if it would work better or worse, but there would be challenges to doing it, because the size has to have good coupling to the ground. On Mars, the gravity is enough to do that, even on a sandy or rocky surface. On an asteroid, you've got the barest movement, and you'll start floating away or bouncing around the surface like the Philae lander on Rosetta did. You need to be anchored to the ground. Once you've solved that problem, you can probably get some really interesting data from a seismometer. And the heat flow probe, definitely useful on a comet or asteroid. The Rosetta mission also included a penetrator of its own. It was a different design, different shape, but it was designed to measure thermal conductivity. The mole could potentially be used on the moon and could potentially be used on an asteroid or comet. But again, you'll have to solve that anchoring problem. Otherwise, it's going to knock itself away from the surface.
How about these standardizing these instruments so that they could be less expensive and used on other bodies or on other missions?
Standardization might be possible if you had a standard set of purpose, of goals. If you're investigating different scientific questions on different kinds of objects, you're probably going to need to go back to the drawing board, at least for some of the major components, and certainly the exterior pieces of how it actually interacts with the surface. The seismometer, it's there are probably aspects of it that could be used on any body, but getting the instrument there and taking the data is only part of the story. Being able to interpret it is another. So I would say it's possible, but I don't think it's likely, at least not anytime soon. We don't have any kind of assembly line process for this sort of instrumentation.
Yeah, it just seems like these are the tools to look at the interior, like a camera. So for the interior. So like being able to come up with a camera that might work on asteroids, say. So you develop a low gravity set of instruments that you could put on multiple bodies or multiple asteroids, and it'd all be the same instrument.
Even cameras for an orbiter, say, are not standard things. Depending on what frequencies of light they're looking at and how long they have to stare at a particular place and how much light they have to collect, whether they're looking at Mars or Titan or the Earth, there's not a one-stop shop for even something like a camera. So like this seismometer, if you wanted to put it on Venus, you couldn't do it. It would not last long enough. You'd have to build it out of something that won't melt in 700-degree temperatures. So you would have to build it out of, make circuits out of diamond or something like that. Maybe it's physically possible, but it's certainly not what this thing can do. Could you send it to Mercury? Yeah. Could you send it to the moon? Yeah, but you'd have to get it there in a different way.
Thank you.
Mm-hmm.
Good evening. Two questions. One, is InSight capable of detecting the presence of liquid water?
I would say no. Where it's landing on the equator, we don't expect there to be any subsurface ice for certain, at least nothing stable. And we don't, there's liquid water, the places on Mars where there might be liquid water, like salty brines that form slope streaks, that's nowhere near where we're going. And I think the abundance of water on Mars is too low for it to show up in any kind of seismic signal. And it would certainly be a big surprise if it would show up in conductivity data, because if water's in the ground, the conductivity goes up very quickly because you've got a lot of that liquid making contact between particles. So if we saw a really surprisingly high number from HP cubed, we'd have to come up with some explanation for that. And water could be an explanation, but I don't think it's likely.
Okay, and number two is, how will the science collected from InSight affect future missions?
Wow. As I mentioned before, every question we answer raises new questions. And so there might be a desire to go back to Mars with a different or additional suite of instruments to help answer some question that we don't even have at the moment. And possibly these instruments, as the previous gentleman alluded to, they could be used on other objects. If these are particularly successful, maybe a mission where the French or German space agencies partner with to Mercury, for instance, would want to bring some redos of these instruments and use them again to answer similar questions, but different because the bodies are different.
Okay. Thank you very much.
Mm-hmm.
Hello, thank you for the lecture. So, for the seismometers, my question is, what if you don't find Marsquakes? What if it's just from the meteorites itself, not from the planet?
That itself, a zero result, if your instrument is working properly and you don't see the things you expect, that's still information. That's still something that you need to explain. And it's going to take a lot of deep thinking to understand why Mars is so quiet. But this is one of the reasons why it's good to have Phobos and have that atmospheric excitation and meteorite impacts. Because we know those happen, and we know we'll see something. But if Mars were that quiet, that would be big news.
Okay, thank you.
We have some questions from folk that are listening to the simulcast. Manu asks, how did you select Elysium Planitia as the landing site? So as I mentioned, size, as a seismometer looking at Mars as a planet, can do its job from anywhere. And HB cubed wants broken up ground. But there are other constraints for the lander. It's solar powered, for instance. It doesn't have a radioactive power source like Curiosity does, so it has to have the sun. And it's supposed to operate for a full Mars year. And we might get dust storms, dust settling on the solar panels, things that would make them weaken over time. So we needed to pick a location where we were going to have plenty of sunlight all year round. So we went to somewhere near the equator. Also, since we're coming down on that heat shield and parachute system, we need to be low enough in elevation that the atmosphere, thin though it is still thick enough for that parachute to do its job. If we landed in the highland regions, that parachute would be not working properly by the time we hit the ground. There are a few other places along the equator that would meet that elevation requirement, but they're really windy, and we don't want that either. We don't want to land in areas that are particularly dusty. We don't want to land in areas that are really rocky. And you add all of these constraints together, there actually aren't that many places on Mars that fit the bill. So this is the reason why Elysium Planitia was chosen, and there's a whole process, a whole set of geologists working here at JPL led by Matt Gollenbeck who have worked to verify that the landing site we've chosen is the best place for us. And then Michael asks, what is the tip of the mole made of? It's made of titanium, and the hammer on the inside is heavy and is made of tungsten. So, Sagin asks, after the data are sent back to Earth, how long before scientists around the world can use them? NASA has rules about this. NASA is a publicly funded institution, and all the data we take from every mission becomes publicly available. All the raw information that comes down from the satellites is put out there for everyone to use. But after a short embargo, there's a short period of time where the data are the province of the scientists that have worked on this mission. Because in the scientific world, getting first access to that data and being able to publish your results is a very important thing for the people who have spent so many years working on this project. So they have a period of time where they have sole access to the data, but NASA has rules that this data must become publicly available in a short period. I think at most it's 6 months, but you have to justify that. For InSight, I think it will be much less than that. And finally, Los Angeles asks, what instruments were considered but didn't make the final payload? It turns out that InSight has been the brainchild of our principal investigator for quite some time, not necessarily with the same name and not necessarily with the same complement of instruments. As it has been proposed in different guises in the past, this mission has had a different complement of instruments as part of its payload, sometimes more elaborate. There was a previous version, I think in 2006, that had 2 moles, just in case one of them ran into a rock. But as this mission has evolved, so we've made choices about what makes it into the mission and what doesn't. So these instruments, what you see here is pretty much what was proposed when the mission first went to NASA in 2010. There are a few additional things. We added, I think, a very sensitive barometer to look for that atmospheric excitation, and we added a magnetometer to determine the local magnetic characteristics. These are small added pieces, and you never do just anything with this big. You never just add a magnetometer. You never just put a piece of tape there. It's always complicated. So there wasn't really a selection process for the instruments. Now, other missions like Curiosity and the mission similar to it, Mars 2020, which we'll be launching in 2020, we hope, did have a competitive process for the payloads. NASA put out a call that said, here are the broad scientific goals we want to address. Feel free to propose an instrument that addresses one or more of them, and then that is competed. The mission itself was not, but the payloads were. InSight didn't quite follow that paradigm. If there aren't any more questions, sir, please.
Have you thought about making an army of bees and sending that to collect more data, a faster way of collecting data, and making that thing sort of like a dock charging device?
Well, flying on Mars is a difficult prospect. It's got a really thin atmosphere. Nonetheless, we are actually working on a Mars helicopter. It's like a double rotor drone that may be going on the 2020 rover. We don't have a way of producing very small motes, sort of individually addressed sensors that can move around the surface of Mars. It would be great to get more data, but again, the seismometer, that's about as small as we can make it. We don't have a device that's that sensitive that can be made so small.
And one more thing. Have you thought about sending water to Mars and see how it reacts? And like salt water, or like, so like how it reacts to
I know the answer to this question really well because I spent 6 years of my life building Mars in walk-in freezers when I was a grad student. I studied the growth and evolution of subsurface ice on Mars, and the whole idea behind that is how does water in Mars's atmosphere and in the subsurface move around. At the present, on Mars, water could not exist in a stable form as a liquid. It would either evaporate or freeze. If you add salt to it, you might get to the point where you can have a really salty brine that could exist on Mars today on a warm day near the equator. But we can understand the physics of water, the physics of a salt solution in an environment like Mars. We can simulate that in the lab, and we know what to expect in those cases. That doesn't mean Mars still doesn't have surprises for us, but it's a big place, and the geologic context. Where did that water come from? Why is it there? That's the important question, not what it does when it's there.
How
many peak watts? The total power produced by the solar rays? I'd have to look that number up, I'm sorry. And with that, we're done. Thank you very much.